In December 1914, the Strand Magazine published a puzzle about consecutively numbered houses. Find a door X where lower and higher addresses have equal sums, excluding X, with n between 50 and 500. Mahalanobis later recalled bringing it to Ramanujan, who looked beyond trial and error. We begin with 8 houses, where every sum is visible. The crucial issue is whether the equal totals meet at an integer door. At house 4, the lower addresses total 6, while the higher ones total 26. House 5 is closer, but 10 still does not equal 21. At house 6, 1 through 5 total 15, and 7 plus 8 also total 15. 6, therefore, balances 8 houses exactly, raising the question of whether more such streets exist. The first non-trivial pair is Street 8 with balanced House 6. At 49 houses, House 35 leaves 595 on each side. At 288, House 204 leaves 20,706 per side. Next comes Street 1681, suggesting a lineage rather than isolated accidents. Door-by-door search confirms examples, but neither explains them nor predicts the next one. Ramanujan's leap was to seek a mechanism carrying one exact solution to another. The repeated 2's ahead are the first clue, coming from the continued fraction of square root 2. From 8 and 6, the square root 2 mechanism advances directly to 49 and 35. The same step then produces 288 and 204. 2's recur because square root 2 has continued fraction 1, followed endlessly by 2's. This previews the engine. Now we derive it from the elementary balance condition. Balanced does not mean centered. 8 houses have midpoint 4.5, yet balanced address 6. What matters is numerical weight, because each address contributes its value. Excluding 6, the lower addresses total 15, exactly matching 7 plus 8. Generally, the sum below x equals the sum above x, with x counted on neither side. As x moves right, the lower total rises, while the upper total falls, creating one real crossing. For 10 houses, it occurs at square root 55, about 7.416. Integer doors 7 and 8 lie on opposite sides, so both fail. A real balance always exists. A puzzle solution requires it to land exactly on an integer. Addresses 1 through 8 contain 36 units, naturally forming a triangular stack. Because house 6 balances, the upper 15 units can copy the lower 15. Those two triangles, plus the 6 excluded units, fill a 6 by 6 square. Thus, the triangular total through n must equal the square of balanced address x. Write the balance directly. 1 through x minus 1 equals x plus 1 through n. Using triangular numbers, these become t before x and t through n minus t through x. Multiplying by 2 and canceling matching linear terms removes the separate sums. The result is 2x squared equals n times n plus 1, or x squared equals t sub n. The street puzzle is now classical. Which triangular numbers are perfect squares? Every balanced street corresponds to a triangular array containing exactly an x by x squares worth of units. Most triangular numbers fail, making square triangular numbers exceptional. The first non-trivial success is 36, both the 8th triangular number and 6 squared. By contrast, 10 lies between 3 squared and 4 squared, so street 4 fails. Adding all 8 triangular rows gives 36 units, so a square must contain every one. A 5 by 5 frame holds only 25. The 11 stranded units prove that 5 cannot be the balanced address. The square side must be exact. Redirecting the 36 units into a 6 by 6 frame fills every position. This is the exact identity. 36 equals 6 squared. Its square root is 6, which returns to the street as the balanced house number. The same test scales to 49 houses, forming a much larger triangular stack. Its total is 1,225. That number equals 35 squared, so the triangle fills an exact 35 by 35 square. Therefore, house 35 balances the 49-house street, the next solution after 8 and 6. Street 50 fails because its triangular total is 21 short of 36 squared. This difference is a residual measuring distance from a perfect square. Scanning successive street lengths moves the residual, but almost every candidate misses 0. The next 0 occurs at n equal to 288, with square side 204. For n equal to 288, pair the outer triangular rows and continue inward. This creates 144 pairs of length 289. Those dimensions are 12 squared and 17 squared. Their product is the square of 12 times 17, which is 204. Thus, the total is 204 squared, making house 204 the balanced address. A finite scan quickly finds the small hits at street lengths 1 and 8. With more work, it reaches 49. Eventually, it records 288. Yet, an empty stretch cannot reveal whether another solution lies beyond the horizon. Computation catalogs examples. Structure must generate the family and prove completeness. From the balance equation, the ratio n over x approaches square root 2 as solutions grow. Indeed, n is the integer part of x times square root 2. For x equal to 204, that product is about 288.499. This mere half-unit offset suggests shifting n by 1/2 to complete the square. View n times n plus 1 as a rectangle whose side lengths differ by 1. Splitting the added strip evenly places half a unit beside each n. Then n squared plus n becomes n plus 1/2 squared minus 1/4. Almost a perfect square. Multiplying the completed square equation by 4 clears the remaining quarter. Set m to 2n plus 1 and q to 2x, then m squared minus 2q squared equals 1. Balanced streets are now integer points on this Pell hyperbola, and suitable positive points convert back into streets. The curve has infinitely many real points, but we need a mechanism producing infinitely many integer ones. The Pell equation demands approximations m over q of exceptional accuracy to square root 2. Its continued fraction, 1 followed forever by 2's, supplies exactly such convergence. Their Pell residuals alternate between -1 and +1. The +1 rail contains every positive solution of m squared minus tq squared equals 1. There, m is odd and q even, so having back recovers integer n and x for every balanced street. The fundamental Pell unit is 3 plus 2 times square root 2. Multiplying any solution by this unit creates a larger one while preserving the value 1. Finding another balanced street now means turning the same algebraic gear once more. Successive powers march through integer points on the hyperbola. Because those powers grow without bound, infinitely many balanced streets exist. After the trivial 1-house seed, the Pell engine reaches 8 houses with balanced house 6. One turn advances to 49 houses and house 35. Next come 288 with 204. Then 1,681 with 1,189. The same exact multiplication continues beyond every visible scale. Beyond the familiar examples, the sequence continues without changing its rule. Street lengths soon pass from thousands into hundreds of thousands and far beyond. Every milestone remains exact because the Pell invariant stays equal to 1. The horizon hides later streets from view, but cannot stop a recurrence that grows forever. We can remove square roots and express the same engine through integer recurrences. Starting with pairs 1 and 1, then 8 and 6, each new pair uses the previous 2. The next balanced address is 6 times the current address minus the preceding address. The next street length is 6 times the current length minus the preceding length plus 2, remaining entirely integral. Feed the 2 seeds into the recurrence, and the first new street is 49. Next come 288 and 1,681, with their balanced addresses generated alongside. Repeated application creates an accelerating cascade of larger integer pairs. Because the recurrence comes from a norm 1 Pell unit, every output satisfies the original balance equation. Return to the bound between 50 and 500. The family selects street 288. Its balanced address is 204, omitted from both sides. 1 through 203 and 205 through 288 each total 20,706. Neighboring Pell solutions lie outside the bound, making this the puzzle's unique street. The bounded answer is therefore one visible member of an infinite family. On an ordinary scale, the solutions fly apart. A logarithmic view reveals regular growth. The half-unit shift in n exposes the same linear Pell transformation at every step. Its dominant multiplier is 3 plus 2 times square root 2, about 5.828. So each street is nearly 6 times larger, leaving few solutions inside any fixed search window. The entire construction now unfolds from the 8-house seed without further searching. The recurrence generates 49, 288, 1,681, and every later street. Each accompanying house balances its two sides exactly. One integer rule solves the bounded puzzle, predicts every larger example, and proves the family never ends. Behind it lies square root 2's endless continued fraction, whose repeated 2's open Ramanujan's puzzle into an infinite world.